Hello everyone. In today's class, we will discuss tokenization strategies. So far we discussed transformer in details, right? We also discussed different types of attention mechanisms. Um, we also discussed pre-training strategies, right? Specifically BERT, and before that we discussed different types of word embedding methods, right? Word to vec, glove, fast text, and so on. So in each of these techniques, right, if you notice it properly, the first and foremost step is to tokenize the streaming words, right? The tokenization is very important because it actually helps you determine which words are similar, right, in a very high level. Okay, so it also helps you understand unknown words very effectively. Okay, so in transformer or before transformer, let's say RNN based methods, neural methods, before and also word to vec, glove kind of methods, the inputs that we give are basically a sequence of tokens. Now before neural language models, what people used to do, people who used to use different types of delimiters to tokenize a running text, right? For example, you use space, you use tab, you use say full stop, you use new line, right? Using these delimiters, you can essentially tokenize a sequence of running text, right? So but then people realized that this delimiters may not be a right approach, because well, in a normal text, when it is okay to split running text into different words based on these delimiters, but when it comes to the testing, right, when you see an unknown token, or a token which is difficult to decipher, right, you may wonder what kind of tokenization we should use, right? So this field, the field of tokenization, has been one of the prior areas in large language models, in neural machine translation, neural language model in general. But so essentially we look at three kinds of strategies, right, for tokenization, that have been used quite heavily in different kinds of large language models. Okay, so before that, today's breaking news is as follows. Microsoft recently released 3.5 family of small language models. This was released in August 20. You can look at this blog post in Azure AI services. So 3.5 mini, 3.5 vision, 3.5 mixed of expert were released. The 3.5 mini version is specifically designed for handling multilingual text with 128K context length. 3.5 vision is a 4.2 billion model. These are all small models. These basically improves multi-frame image understanding task, and the 3.5 MOE, right? This basically features 16 different experts, and this is a 6.6 billion parameter size model. Okay. Now in all these methods that was proposed here, you see that these methods actually have undergone further pre-training using different types of strategies like multilingual synthesis, high quality filtering, and so on and so forth, with human alignment like SFT, PPO, DPO, and a combination of various things, human labeled, synthetic, and translated dataset. So this is the link. As I mentioned, you can go through the link and you can download these models. Okay, so coming back to the topic again, tokenization. So the word level tokenization, the strategy that was there before neural machine translation, neural language model, right? Word level tokenization is not good enough, because if you think of words, right, what is basically a combination of characters. Now you can think of an exponential number of words possible, right? If you think of the fixed set of characters, Now, with this fixed set of characters, you can think of exponential number of words. So it may be possible that some of the words are not meaningful words, some of the words are meaningful words, but you can think of, you know, a lot of such words, right? So only words as a token may not be a right approach, whereas a character as a token also may not be a right approach, because if you think of only a character, then there's a fixed set of characters that we can think of, right? 26 characters and maybe some special characters like hash, at the rate, like some unicorns and symbols like that. So that may be a limited set of vocabulary, whereas if you only consider words, right, that is also a huge set of vocabulary. Now, you can also imagine new words which are not part of your training set, right? Remember, when you talk about tokenization, this tokenization is performed during the training phase, right? So during the training time, you basically go through the entire corpus and you identify the vocabulary, and that vocabulary will help you parse an unknown token during the test time. Okay, so in between character level tokenization and word level tokenization, we can think of subword level tokenization, right? If you remember the word embedding method, we talked about you know, word to vec, glove, and fast text, right? Fast text is essentially a subword level tokenization, subword level embedding methods, which basically uses a subword level tokenization strategy. Okay, so now why this subword level tokenization is even more important. Now let's say if you have a verb, right, let's say catch, and let's say catch, okay, and catching. Now let's say in your training set the word catch is present, but the word catching is not present, right? But in a test set, when you parse this word catching, right, you will not be able to split it properly, because you know that in your training set it is not present, right? But let's say if you think of subword level embedding, and let's say one subword token is catch, right? Then you can say that, okay, in the test token which is catching, you can split it into two parts, catch and ing. And since the word catch is also present here, maybe the word catch and catching, these are kind of similar, you know, appear in the similar context, and so on and so forth, right? Similarly, let's say another word, let's say hugging, right? Right, and let's say this is the split, hug, HUGG, for example. Again, it's a hypothetical split, and ing. Okay, now you know that that in your test set ing is present. In your training set, let's say hugging is present, where you know that ing is also part of hugging. So you can essentially say that, okay, maybe the word catching and hugging is similar. The word catching and hugging, they are similar in some context. Maybe they are both of them are actually continuous tense, right? So therefore we will basically break a word into subwords, right? Tokens into subtokens, and so on and so forth. And then these subwords basically form tokens, and these tokens are basically fed to the neural model, to the transformer, to the RNN, to the word to vec, and you know, any other models that you can think of. Okay, so this is by the way, tokenization is an active research area. So in this lecture, we will look at 3 types of tokenization techniques: Byte-Pair Encoding, WordPiece encoding, and Unigram Language Model tokenization, which is used in sentence-piece encoding. Sentence-piece encoding. Right? We will discuss these 3 kinds of techniques in this lecture, and we will see that all modern LLMs like BERT, T5, right, GPTs, they essentially use this, one of these methods or a combination of these methods. Okay, so in each of these methods, we will see that there are 2 basic steps. The first step is basically a token learner. The task of this token learner is to learn the tokens which will basically form the vocabulary. Okay, and this token learner is executed during the training time. So during the training time, we run this token learner, which will essentially learn or identify the tokens which are going to be a part of the vocabulary, right? Then during the test time, we use another module called token segmenter, right? This is during the test time. Remember, in the training time, you already identified the vocabulary. In the test time, based on the vocabulary and maybe a set of rules that you have identified, right? You can further you can tokenize a raw test sentence into different tokens. Okay, and token segmenter is responsible for this. Okay, now for byte-pair encoding, you have one type of tokenizer, one type of segmenter. For WordPiece, you have a different type of tokenizer and segmenter. For Unigram language model segmentation, tokenization, you have again different types of tokenizer, learner and segmenter. Let's start with byte-pair encoding. In short, it is called BPE. Okay, very simple idea. So byte-pair encoding was originally proposed for text compression techniques. Okay, for text compression strategy, it was proposed in long time back, and then in 2016 in the ACL paper they used this this technique for neural machine translation. Okay, and byte-pair encoding is used in methods like GPT, GPT-2, Robota, bot, BART bot, right? This is a different bot, by the way. This is a encoder decoder model, right? We'll discuss later. And then Robota and so on. Okay, so let's look at the algorithm. So this is the algorithm. It's not very important. You will understand the algorithm once we describe the method. Let's look at the method first. Okay, so essentially there are three steps. The first step is that, now remember, as I mentioned earlier, you have basically two different modules, right? One is this token learner, other is this token segmenter. The task of the token learner is to identify tokens. Okay, to identify tokens, what we do during the pre-tokenization stage. Now, pre-tokenization stage is a stage which is executed before the token learner is executed. Okay, now during the pre-tokenization stage, what we do, we clean the corpus, right? We are given a training set. We clean the corpus, meaning maybe we remove punctuations, maybe maybe we remove some special characters. We normalize the text, meaning we convert all the lowercase to uppercase, uppercase to lowercase. Again, these are not very standard steps, by the way. All these things are dependent on the application, right? But during the pre-tokenization stage, you clean the corpus, you break words. Let's say you break a sentence into words, right? You break sentence into words based on space, punctuation, more complex rules, and so on and so forth. You can use traditional NLP techniques for doing that. Okay, now once we do that, once your cleaning process is done, you essentially identify all the words, right? So all the unique words that are there in the corpus, right? Now all these unique words basically are tokens, are types, right? All the types have been identified now. Okay, now then what you do, once it is done, we create a base vocabulary. What is a base vocabulary? A base vocabulary is essentially the starting point of your segmentation process, of your tokenization process. In the base vocabulary, what you do, you essentially add all the unique characters present in the tokens that you identified so far, right? So you have all these words. From the words you identify, you basically extract the characters and you add those characters into the vocabulary, right? For example, one word is hello, H-E-L-L-O. You add the character H, E, L, and O. You add L one time because you want to add only unique character, right? So H, E, L, O will be added to the vocabulary. If there is a special symbol, let's say dollar or hash, these will also be added to the vocabulary, and so on and so forth. Okay. So now, in the best case, what would happen? In the best case, you basically ended up adding all the unique characters present in a language, right? In English, let's say you ended up adding all 26 characters. Assuming that all 26 characters appear in the corpus, in your training corpus, at least once, right? So now this is my base vocabulary, and what I do, I keep on increasing this vocabulary size with more and more training. Okay. Okay. Now, what is the step? What is step 3? Step 3 is merging, right? Then what we do, once we identified the base vocabulary, what we do, we look at all combinations of these characters. So far we have H, E, L, O, these 4 characters. Then we look at all possible combination of characters. We start with bigram, right? Bigram character. Let's say HE, right? EL, HL, HO, LO, and so on and so forth. All possible characters, all possible character combination, and we choose that particular combination whose frequency is high in the training set. I'll explain what is the meaning of high frequency, right? Let's say, for example, in our example, let's say the combination LL, right, appears most frequently, right, in the bigram, right? So LL is basically the most frequent bigram character in the training set. We merge L and L, and that will become a vocabulary entry now. Okay. So let us take an example and explain this. But before that, so we keep on merging this thing until and unless a specific size of the vocabulary is reached, right? Let's say we predefine the size of the vocabulary to be, let's say, to be 1000, right? So we keep on merging bigram, trigram, 4gram, and so on and so forth, and we stop when we see that the specified size is achieved. Okay. All right. Let's say these are 5 words: cat, bat, bag, tag, and cats. Okay, these words are present in the training set, right? And their frequencies are as follows: 10, 5, 12, 4, and 5. So the word cat appears 10 times, word bat appears 5 times, and so on and so forth in the training set, right? Okay. So to start with, what we do, we first identify the base vocabulary, right? Base vocabulary is identified from the characters, unique characters present in this corpus, right? So unique characters are A, B, C, G, S, and T. So this is my base vocabulary. Okay. Then we look at combinations. We look at the combination and the frequency, and based on the highest frequency, we merge that particular combination, right? So how many combinations are possible? AA, AB, AC, AG, AS, and AT. Then again BB, BA, right? All possible combinations that you can think of. Okay. So let's look at it here. So the word cat, bat, bag, tag, and cats, these are the tokens present, right? So initially, as I mentioned, the unique characters are part of the vocabulary. So the character cat, C, A, T, G, S, these are part of the vocabulary now, right? C, A, T, G, S, B also. Now we look at all combinations. Some of the combinations are listed here. Let's say CA, right? CA, by the CA and AC are different. Okay. CA, this token pair, the frequency is 15. Why this is 15? Look at it here. CA appears in the word cat, and the word cat appears 10 times. That means the combination CA also appears 10 times in the word CAT, right? CA also appears here in the word cats, right? So the total appearance of CA is 10 plus 5, 15, right? Similarly, another combination is AT, 5 times here, right? 5 times here, and 10 times here, right? So the frequency is 20, and so on and so forth. We calculate all bigram characters and their frequencies. Now here, which one is the highest, right? The highest is AT, right? So therefore, we combine A and T with this new split rule, which is A plus T goes to AT. So this is the new split rule that we learned, right, from this table. Okay, so once we identified this, what we do now, all the appearances of A and T, A comma T, will be replaced by the new vocabulary word which is AT. Remember, AT is new vocabulary word, so AT will be added here. So this is a vocabulary V, right? So A and T will be added here, and all these combinations will be replaced by the unique token AT. Okay, now look at here, C AT. It is not C comma A comma T. This is C comma AT, B comma AT, right? C comma AT comma S, and so on and so forth. Okay, so what we did, we select the most frequent pair AT, merge them into a single symbol. A single symbol is now AT. Add this newly created symbol to the vocabulary AT. But remember one thing, the earlier symbols which were used to create the new symbol A and T, they are also present in the vocabulary. It is not that we removed those two symbols A and T and we removed them by another, we replaced them by another new token AT. No, those are also there, and along with those you added a new token which is AT. Okay, all right, now we learned a new rule which is A plus T equals to AT. A comma T leads to AT. Now these rules are important, right? We keep on collecting these rules, we keep on expanding the vocabulary, we keep on collecting these rules. Okay, now look at here. Now this is my modified table, right? In the modified table, again we keep on combining. Now here, what are the combinations possible? Again, it depends on the vocabulary, right? My vocabulary is this one, A C T G S B A T, A C T G S B A T. How many possibilities are there? Again, AC, AT, AG, and so on and so forth. Bigram possibilities are there. Trigram possibilities are also there, right? You can merge A with AT, AAT, right? C with AT, CAT, and so on and so forth. Bigram and trigram possibilities are all there. As you see, this is a bigram possibility, and these are trigram possibilities, right? This is again another bigram possibility, and so on. This is a partial table, by the way. So if you merge AG, right, look at the frequency. AG appears here with the frequency 12, AG is here with the frequency 4, so totally 16. What about cat? If we merge C and AT, 10, C and AT, 5, 15, right, and so on and so forth. Again, what is the highly frequent token pair, which is AG in this case, right? So we repeat the same thing. We learn a new rule, A comma G derives AG. Initially earlier we learned A comma T derives AT. Now A comma G derives AG, right? And what else we do? We replace all the occurrences of A comma G by AG. So this is going to be B comma AG, this is going to be T comma AG, and so on and so forth, right? This is my modified frequency table. This is the modified vocabulary where you see both this new new tokens have been added, right? And these two roles, the two rules have also been added. Okay, now again we do the same thing. We keep on merging. It can be 4gram now, right? As you see here, cat plus S, right? Trigram, 4gram, right? And you see here the most frequent merging could be the most frequent token can be cat, right? With the rule C comma AT derives CAT. Okay, so the word cat will now be added to the vocabulary, right? AT along with AT and AG, a new token which is added is CAT. Okay, so all appearance of CAT will now be replaced. C comma AT will be replaced by CAT. Okay, so we learned three rules: A comma T derives AT, A comma G derives AG, C comma AT derives CAT, right? And what is my my final vocabulary till this stage? The final vocabulary is this one: A B C G S T, right? A B C G S T, then AT, AG, and CAT. Okay, we keep on doing this thing until unless the predefined threshold of this vocabulary is reached. Let's say the size of the vocabulary that we are expecting is 1000, right? We keep on expanding and we stop when this predefined threshold is reached. Okay, now let's see what happens during the test time, right? So this is essentially, you remember, again I'm going back and forth, token learner. So this is the task of the token learner. So whatever I discussed so far is the task of the token learner, to learn the token and the vocabulary. Now we are executing token segmenter, right? What the token segmenter will do, whatever was learned in the tokenization stage, that rules, that vocabulary will be used to segment unknown tokens. Okay, so let's say the word is bag, BAG, in your test set. Okay, token segmenter will be executed here. So what it would do first? It would first split the word BAG into so it basically should be BAGS. I think there's a typo here, BAGS. Okay, so it first segment the entire word into characters B, A, G, and S, and then it will start applying the set of rules that we have learned so far. But remember, the set of rules are applied in sequence, right? We'll first apply this, then this, and then this. The way we curated the rules, the same way we basically apply these rules, execute the rules. It is not the case that we first apply C comma AT and then A comma T. No, the way we applied the rule, the way we curated the rule, the same sequence will also be used to execute those rules. Okay, so we go through the merge rules, right, until we'll find we basically we find one that we can apply. For example, right, if I apply A comma T derives AT, it is not there, right? If I apply A comma G derives AG, this can be applied here, right? So A comma G will now be replaced by AG. Okay, so A, now the modified, the updated set of tokens will be B comma AG comma S. Now let's see whether I'll be able to apply some other rules or not. Of course, C comma AT will not be applied. So the updated or the final tokenization, the final tokens for the word BAGS is going to be B comma AG comma S. Okay, and this will be fed to the transformer or to the RNN method, right? Now what happens if a token is not present, right, in the vocabulary? Now remember, here in this case, all the tokens B, AG, and S, right, B, AG, and S, they are part of the vocabulary, right? All three are part of the vocabulary. But let's say you have a word MUG, right? The word M, the character M is not present here, right? The character U is also not present here. How do you deal with this during the test time again? Let's see. Okay, let's say the word is mat, M-A-T. Okay, and again we start applying the rule, right? First M-A-T will be split into A comma A, M comma A comma T, right? Then we apply the first rule, M comma A comma T, right? Then we apply the first rule which we learned, which is a comma t derives at, right? So a comma t will be replaced by at. Now I have two tokens m comma at. Now I can't apply other rules. So the final token should be m comma at. But the token m is not present in the vocabulary, right? So if it is not present, we also don't know its corresponding embedding, right? Think about what to make. Think about a transformer. In transformer, when we feed all the tokens, we basically feed their corresponding embeddings, right? So m is not present in the training set, m is not present in the vocabulary, therefore m doesn't have any embedding, right? What we do here, we replace all such unknown characters by a token called unk. Okay, so this unique token unk is always a part of the vocabulary that you have learned. Okay, it is always a part of the vocabulary that you have learned so far, right? The base vocabulary must include every possible character or a symbol like unk. Okay, so this will be replaced by unk, and then you already know the embedding for at because this is a known vocabulary entry. So this is going to be my tokens for the word mat. Clear? In this way we deal with unknown. We will see in case of WordPiece we have a different strategy. In fact, in GPT-2 and Robota, what they use basically bytes, the byte concept instead of characters, right? These bytes are basically parts of their base vocabulary, and then on top of this they keep on applying these rules. Okay, so this is a simple version of BPE, Byte-Pair Encoding. Of course, you can think of modifications, further modifications on top of this. Let's move to the next part, which is WordPiece tokenization. The idea behind WordPiece tokenization is very same as BPE, right? The only difference is that here the merging operation, merging of two characters, merging of two tokens into subtokens, right, is not performed based on the frequency, right? It is performed based on another property, right? Another formula that we'll discuss here. So in WordPiece, we merge based on something called the likelihood, not frequency. How do we define likelihood? We'll discuss. So this WordPiece tokenization is used in BERT, the Google's BERT paper, Distill BERT, Mobile BERT, Funnel BERT, and MPNet, and so on and so forth. Right? This was proposed way back 2012, and then I think later on it was modified for the task of language processing. Okay, so let's look at the steps here. It again has two steps. In the first step, during the training time, right, we have this training corpus, training document, and from the training document we identify the vocabulary, we identify the rules, and so on and so forth, right? And then during the test time we apply this, we use this vocabulary and rules, right, for splitting a word into subwords. So here what we do, remember in the BPE what I mentioned, let's say a word hello, HELLO, right? It was split into HELLO at the beginning, right? Character level split. But here what we do, we use a special character double hash, right, to indicate, to differentiate between the character which appears at the beginning of the word and the characters which appear in the intermediate part of the word, right? So here the word HELLO will be split in this way: H, comma, double hash, E, comma, double hash, L, comma, double hash, L, comma, double hash, O. The double hash is a prefix. This indicates that the token is an internal token, not the beginning of a token, right? Okay, so similarly the word token will be split into t comma double hash o double hash k double hash e double hash n, right? Now for every, so when we think of merging, right, we use, let's say we want to merge two characters c and d, right? In case of BPE, what we did, we looked at the frequency of CD. Here what we do, we use this core function. This is very simple. Frequency of CD divided by frequency of C times frequency of D. This is a kind of mutual information, PMI, pointwise mutual information that we generally discuss in the semantics of NLP. Okay, so this is kind of my likelihood. Okay, so frequency of the pair divided by frequency of the first token times frequency of the second token. What is the beauty of this one? The beauty of this core is that, let's say, even if a pair is highly frequent, if their corresponding constituent characters are also highly frequent, that specific pair will be penalized, right? Versus, let's say there's a case where the pair is, not that frequent, kind of medium frequent, right? But the tokens are not, their corresponding tokens are not that frequent. That particular pair will be given high priority. We'll discuss with an example. Okay, so step 1 and step 2 are the same as we discussed in case of BPE, right? Step 1 is basically a pre-tokenization where we clean the corpus, we split the sentence into words based on space, characters, based on space tabs, some other unicorns, and so on and so forth. Step 2, we identify the base vocabulary. Base vocabulary, in our case, again, the base vocabulary constitutes all these tokens, right? All these characters. But remember here, characters are differentiated based on the positions. If a character appears at the beginning, it will be added to the vocabulary without hash. If the character appears at the middle or the end, it will be added to the vocabulary with a prefix of double hash. Okay, now step 3 is the merging. What we do here, we choose the symbols that maximize the likelihood of the training data when added to the vocabulary. Okay, what is the merge criteria? The algorithm identifies the symbol pair whose merge would maximize the likelihood of the training data. This is determined by selecting the pair with the highest score, the score that I discussed earlier, defined as the probability of merged symbols divided by the product of the probabilities of its individual components. Okay, and again, similar to BPE, we stop the method when a particular size of the vocabulary is reached. Let's again take an example. Okay, so let us assume that these are the training words, words present in the training corpus: sunflower, right, flow, flowers, and so on and so forth, and the corresponding frequencies. Right, now when we segment, right, as you see here, sunflower, sun, hashtags u, hashtags n, hash, right, sun, hash u, hash n, and so on and so forth. As I mentioned earlier, right, all the initial characters will be there without hash, and all the intermediate characters will be there with hash. And what is the vocabulary now? The vocabulary is this one. You see here, there are two unique starting characters, S and F, right? And all the other characters are intermediate characters. Therefore, they are preceded by a prefix. A prefix is double hash here. Similar to BP, here also I start with merging a pair of characters, right? For example, S and U. Let's look at S and U. So S and U, right? So S and U, so the bigram SU, right? What is the frequency of this bigram? The frequency is 1 plus 2, so 3, and then is there any other S of S and U? No, right? So the frequency is 3. And what is the frequency of S? the frequency of S is 1 plus 2 3 plus 2, right? 1, so 3 3 4 4 and then 6, right? So 6 times what is the frequency of U? Frequency of U is 1 plus 2 3, so 3 and then that's all, right? So 3. Okay, so the score for SU is basically 1 by 6, right? You look, the calculation may be wrong, but I hope you understood the concept. So so similarly, we merge UN, UF, FL, LO, and so on and so forth, right? And we obtain the corresponding scores. Here again, you basically identify that pair whose score is the maximum. In this case, S and U, right? S and U will be merged, and the new token will be formed, which is SU, right? Now here, important thing to note is that when you merge S and hash U, right, the resultant token is not hash SU, right? This is only SU. Why? Because S is basically the initial character. But let's say if you had merged U, let's say if you merged this one, if you had merged this one, the resultant character would be UN, because both U and N are the intermediate characters, not the starting character. Okay, so in this case you identified S and U, you merged them, and the new vocabulary word is SU. Okay, so SU is a new vocabulary word along with the previous words, previous tokens present. By the way, I am misusing the term word, right? I'm basically using the term word and tokens interchangeably, but I hope you understand. So once this is identified, then what we do, again similar to the BPE, I replace all S hash U will be replace this by SU, right? All appearances of SU will be replaced by SU, and so on. Okay, so this is my modified table. Again, on top of this, I apply the same set of rules, right? Bigram combination, trigram combination. You see here, these are trigram combination, these are bigram combinations, right? And let's say in this case there's a tie, right? So we can break the tie by choosing one of them. So let's say in this case we chose E and R to be merged. So E and R will be merged, and the new token will be hash ER, which will be a part of the vocabulary. Okay, hash ER is a part of the vocabulary now, and we replace all of appearances of E comma R by hash ER, right? And so on and so forth. So your vocabulary size gets increased, right? The table gets modified, and so on and so forth. The next stage, you again merge ED, right? It will be added here, vocabulary size increases, and so on and so forth. All right, so this is the tokenization step for WordPiece. Now, so this is the training time. Now what happens in the test time? So this is very important. During the test time, remember in case of BPE, what we did? We first split a word into characters, right? And then we applied all these rules one by one in sequence, right? And then we kept on combining characters based on these rules, right? And through that process, we ended up basically splitting the word into tokens. We used the tools in case of BPE, right? Here, in case of WordPiece, we will not use any rule. We will not store the merge rules. We will only store the vocabulary. That's the difference here. We will not store the rules at all. We will only store the vocabulary, right? Now, if we have only the vocabulary, the updated vocabulary that we obtained from the training set, how do we split an unknown token into subtokens, or a test token into subtokens? Let's see. So for that, WordPiece identifies the longest subword available in the vocabulary and then performs the split based on the subword. Let's see. Let's say the word is fused, FUACD, right? And let's say this is my vocabulary that we have already learned from the training set. Okay, we don't have the rules. We haven't stored the rules. So here, if you start from the beginning again, you start from the beginning, right? If you look at the vocabulary here, what is the longest subword, or what is the longest subword which is present in the vocabulary? So if, let's say you start from if, right? If is present here, of course if is present, but if may not be the longest. Let's look at if u. If u is present here, does if u present here? If u is so if u is not present here, right? So it means that the longest subword here is if, right? If u is not present here. Of course, if u is not present, if u is will also not be present. So we split first fused by if. So this will be split into if USED. Of course, this hash. Okay. Now I know that this is the longest one that is possible, so I keep this thing aside. Let's look at this one. Can we split this further? What is the longest sequence here? USED. So of course, if we consider only hash u is present here. What about hash US? Hash US is also present here? No. That means from here also the longest subword is hash u, and the remaining part will be separated. Now let's look at this one. Hash SED. Okay, of course, double hash. What about hash SED? Hash S is present here? Yes, hash S is present. What about hash AC? As hash AC is not present here. That means again the longest word which is possible here is hash S, comma, hash ED. Let's look at this one again. Okay, hash ED is present. Yes, hash ED is present here. Okay, so the final tokens that are derived from fused is if, hash u, hash s, hash ed. Okay, we haven't used any merging rules, right? What we did here, very simple idea. Given a word, right, we start from the beginning. We look at what is the longest subword present in the vocabulary. Let's say, again hypothetically assume that the token if u was present here. The token if u was also present in the vocabulary, right? If it was the case, then the tokens would have been if u, comma, hash sed, right? But this is not the case here. So we start from the beginning, we look at the longest subword which is present in the vocabulary or not. If it is present, we segment that part and again process the remaining part of the word similarly, right? We don't need to store the merging rule, which is useful in our case because we can basically save a lot of memory. What about the unknown word? Let's say the unknown word is funny, funny. Again, this is my vocabulary. I start with if. So the word if is present here. The word if is present here, but the word if u is not present here. So the longest word is if, right? Then let's say if, right? You split it into tokens. If, then so if, then hashtag hash UNNY, right? Again, maybe the unique token is, the longest token is hash u. So if, then hash u, and then hash, the remaining part is hash NY, right? Hash N is not present, but hash N is present. So if hash u, hash N, hash N, and the remaining is hash y. Let's look at hash y. Hash y is not present here. So hash y is not present here. It is not present. What we do here, what we did in case of BPE, we replaced this by the token UNK, right? In case of BPE, the tokens were F, U, N, N unknown. But in case of WordPiece, what we do, the whole word is tokenized as Ankh. Okay, I replace the whole word by the token UNK, not the subword. Okay, the entire token, the entire word will be replaced by UNK. If a specific token, a subtoken, right, is not present in the vocabulary, the entire word will be replaced by UNK. That's it. That is about WordPiece. Now let's move to the next part, which is Unigram tokenization. So in Unigram tokenization, it's a bit complicated, okay, but it's a very interesting idea. So in this tokenization, so this is used in a specific embedding encoding method called sentence space, right, which is heavily used in recent methods like T5, Embed, XLNet, and so on. So the idea here is that we will go back to the concept of Unigram language model, right? I hope you remember what is a Unigram language model, right? We discussed in the language model introduction chapter, given a sequence of tokens W1, W2, .wn. When we measure the probability of the sequence, this token, this is basically a multiplication of all individual tokens, right? P of W1 times P of W2 and so on and so forth. Probability of all individual tokens. We assume that all these tokens are independent of each other. So we use the same Unigram language model concept here while segmenting a word into subwords, right? What is the motivation here? The motivation here is, if you remember the discussion that we had today, right, BPE and WordPiece, both these algorithms produce a single type of segmentation for a specific word. For a given word, you have only one type of segmentation. But in real world, it may not be the case. A word can be segmented into in multiple ways. There can be multiple ways through which you can segment a specific word. So in this Unigram tokenization, what we do, we introduce multiple subword candidates for a particular token or for a particular word during training, right? And here we will use the concept of expectation maximization, EM algorithm. So EM, as we know, it's a very interesting idea, right? We generally used in non-parametric estimation and so on and so forth. If you are not aware of EM, you go back and check the machine learning course, right? For example, the algorithm k-means this algorithm uses EM algorithm for defining the centroids and so on. Okay, so expectation maximization is used during tokenization. Let's see. So again, similar to the previous methods, the first step is to identify the base vocabulary. Now here, this Unigram language model tokenization is different from the other tokenizations that I discussed today. How? So in both Byte-Pair and WordPiece, our goal was to increase the vocabulary, right? And so we started with a base vocabulary and we kept on increasing the vocabulary until unless we reach a certain threshold size of the vocabulary, right? Here, this is just the opposite. We have a massive base vocabulary and we keep on reducing the vocabulary. We keep on shrinking the vocabulary until unless a specific threshold is reached, right? There we increased, here we decrease. So to start with, during the initialization stage, we can use different types of methods to basically get all possible combinations of vocabulary tokens that are possible. For example, you add all the characters, you add all the subwords, possible substrings, and so on and so forth into the vocabulary. And then we decide that out of this tokens present in the vocabulary, which tokens are useful, which tokens are useless. Okay. So here what we can do, we include all the characters, all possible, all frequent, medium frequent substrings into the vocabulary. We can also, here you can also run BPE, for example. You can run BPE exhaustively, right, to create the base vocabulary. Okay. So once we did this, the next stage is essentially to compute the log likelihood loss. Okay. So what is this log likelihood loss? The log likelihood loss is computed based on this Unigram language model. It's better to first, I think, let's look at example, and then we go back to the algorithm. Let's assume that these are the training words: run, bug, fun, and sun. Okay, and these are the frequencies. Let's say we start with this vocabulary, right, where R, U, N, RU, UN, B, G, these are present. There is no hash used here, by the way. Okay, these are kind of vocabulary tokens used in BPE, right? Therefore, I said that we can just run BPE initially at the beginning to curate the initial vocabulary for Unigram language model tokenization. Okay. Then what we do, now these are my vocabulary words: R, U, N, RU, UN, B, G, and so on and so forth. Initial vocabulary tokens, right? And these are the frequencies. U for R, this is 3, for U 31, and so on and so forth. We will not use this raw frequency. We will use unigram frequency. Okay, what is the unigram frequency? What is the unigram probability here? Unigram probability for R is 3 by the sum of this. What is the sum of all the tokens? Let's say the number is 155. The sum of all these frequencies is 155. So the probability here, unigram probability, is 3 by 155. This is 31 by 155, and so on and so forth, right? For example, for the token SU, this is 10 by 155. Okay. So we started off with a base vocabulary. Now for each vocabulary entry, we calculated the unigram probability. Then what we do? Then now for every word present in the training set, we measure the probability of a specific segmentation. As I mentioned, a particular word can be split in different ways, right? For example, the word run can be split into R, U, N, or R, U, N, or R, UN. Remember, R, U, N, RU, UN, these are all vocabulary entries already present in the initial vocabulary. So the word RUN can be split in three different ways. Now let's look at the probability of each of these individual splits. The probability of this split is, as I mentioned, this is unigram probability, meaning all the unigrams are independent of each other. So probability of P, U, N is probability of P. Probability of R, U, N is probability of R times probability of U times probability of N. And how do we get this PR, PU, PN? We will get PR, PU, PN from here. This is PR, this is PU, this is PN. Right, so this time, this time, this is going to be the probability for this split. For the second split, which is RU, N, RU and N, the probabilities will be PRU times PN. PRU will come from here, PUN will come from here. Right? So this is the probability for this split. For the last split, which is R, UN, the probability will be PR times PUN. Again, we go back to the table and we will see the probability is this one. For every word, I look at all possible splits with respect to the vocabulary and their corresponding probabilities. Now from this we identify the best split, right, according to this probability. So the best split here can be, so look at this one, these and these both are highest and the same, right? So let's say we randomly choose this one RU comma N, right, as the base split. So for the word RUN, so far the base split is RU comma N, right? Now think about it. This is very exhaustive, by the way. It's not a very computationally efficient method, right? For every word, coming up with all possible splits based on the vocabulary, it is quite tedious. So what we use this Viterbi algorithm. I'll not discuss Viterbi here, but you go back and check. Viterbi is a very standard method that we generally used in sequence modeling and in many other places. So we use Viterbi algorithm to make the entire computation efficient, right? But at the end of the day, the end goal is to measure the probability for every split, right? So for the word run, right, for the word run whose frequency is 3, the base split that we identified is RU comma N, and the corresponding probability is this one. Similarly, for the word bug, which is present in the training set, let us assume that the base split that we identified is BU comma G, and this is the score. For fun, FU comma N, this is the score. For sun, SU comma N, this is the score. Okay, so for every word in the training set, we identify the base split and the corresponding probability. Then we compute a loss. Okay, what is the loss? Here loss is the log loss. Very simple, log loss. For every word I know the probability, right? I basically take the log of the probability, right, and minus. So minus log loss, minus log of this probability. Why minus? Because this probability ranges between 0 to 1. Log of that probability will always return minus, therefore minus and minus will cancel out. So for every word I compute minus log loss, right? And since the word is present, let's say the first word run is present 3 times, so this will be 3 times the minus log loss, corresponding minus log loss. Similarly, for the word bug, log minus log of this times 5. For the word fun, minus log of this times 13, and so on and so forth. So this log loss essentially is the loss for the entire corpus of the training set, right? Because these words are taken from the training corpus, right? Essentially, when we are combining everything in the log loss, it is basically the log loss of the entire training corpus. Now, the log loss, current log loss is 66.102. As I mentioned, we will use EM algorithm, right? If you do not know what is EM, let's forget about EM. Let's assume that there are 2 steps, M step and E step. Okay. So, what is the goal now? The goal is my goal is to remove a vocabulary entry which is not useful. Already the vocabulary is significantly large. We started with a large base vocabulary. Then at every stage we identify the token in the vocabulary which is not useful. How do we do that? Let's see. So far this is my token frequency table, right? In the based on the vocabulary, in the vocabulary I have R, U, N, RU blah blah blah, and these are the corresponding probabilities, right? Unigram probability that I mentioned earlier. This table is something I already showed earlier. Let us assume that I want to remove UN. I want to remove the token UN from the vocabulary. If I remove the token UN, so for the word RUN, remember initially I mentioned that there were 3 splits, possible splits. One was RUN, the other was RU comma N, the other was R comma UN, right? So this split will not be possible then, because if we remove UN, this split will not be possible, right? So there are only 2 splits that are possible, R, U, N and RU and N, right? Then for these 2 splits, I measure the probability. In the same way, right? probability of R, probability of U, probability of N based on this table, right? Probability of RU, probability of N. Now out of these two splits, which one is the best? This is the best, right? So for RUN, now, so for RUN, the split that that is the best at this moment is RU comma N if we remove UN. Okay. Similarly, for bug, for fun, right? For sun, look at here. For fun, one split could have been F comma UN, right? But since we removed UN, we just need to discard that option. So then maybe the base split will be FU comma N, right? Similarly here, SU comma N, and so on. So UN is a possible token from the vocabulary that I want to remove, right? If I remove, these are the resultant base splits and these are the corresponding probabilities, right? Again, what is the total loss? The total loss of the corpus with respect to the corpus is the frequency times minus log loss. So this log of this minus log of this times 3 minus log of this times 5 and so on and so forth. So this is the total log loss now after removing UN. Now remember this number 66.102. Earlier it was also 66.102 when the token UN was present in the vocabulary. After removing it, it is still 66.102, meaning removal of the token UN doesn't affect the log loss at all, right? So I can safely remove this token from the vocabulary. In fact, if you do this calculation, you will see that there are many other candidate tokens that can be removed, right? UN was one of the tokens, well, I mean, one of the possibilities. RU can also be a possibility. BU can also be a possibility. UG can also be a possibility. In fact, removal of each of these tokens from the vocabulary will not change the loss at all, right? So now out of this, which one I should remove? I can choose one randomly, one of this randomly, right? In fact, what the algorithm does in practice, it removes 5 to 10% or 10 to 20% of vocabulary entries at one go, right? If you see all these tokens are useless, you remove them at a time. Okay. So, but let's assume that in our case we remove this one by one, right? So let's say we select UN and we remove UN, right? And then we basically modify the table. So in the maximization stage, what we did, we removed basically a token. We aim to remove a token whose removal will not affect the loss, or whose removal will affect the loss least affect the loss. Now, once we removed UN, this is the modified table now. This is the vocabulary RU, RUN, RU. Look at here, the token UN is not present at all, and the corresponding frequency. Since you already removed the token, the corresponding bigram probability will also change, right? The corresponding bigram probability will also change. Okay, so now the resultant bigram probability is this one, right? Now let's look at the split again for these words RUN, run, bug, fun, and sun. Let's assume that the base split for RUN is RU comma N, right? For BUG, BU comma G, for FUN, FU comma N, for SUN, SU comma N, and these are the corresponding probabilities based on this table. Okay, again I measure the loss, the total loss. The total loss is the frequency times minus log loss, and now the current log loss is 61.115, 61.155. Okay, now let's see which one I want to remove. If I remove RU, right? So among these tokens, this is the vocabulary. If I remove RU, the loss will be 63.0126. Remember this number, 61.155. If I remove RU, this will be the loss. If I remove BU, this will be the loss. If I remove UG, this is the loss, and so on and so forth, right? Now look at here. The token BU, if we remove this token BU or UG, it will not affect the loss at all, right? So I can remove both, either both BU and UG, or I can remove either BU or UG, right? So I keep on removing vocabulary entries in this way, and then I stop when I see a certain vocabulary size is reached. So let me recap what we discussed here in this specific algorithm, Unigram Language Model tokenization. So I am given the training set, right? From the training set, I did all this pre-tokenization. I identified all the words, right? From the words, I then identified the base vocabulary. The base vocabulary in this case is the largest one, is the longer one compared to BP and WordPiece, right? Because here the aim is different. Here the aim is to basically remove the vocabulary entities which are not useful. So what we can do, we can either you can either add all possible characters, subwords that you can think of out of the words present in the training set, right, and make a larger kind of vocabulary. Or you can run BP or WordPiece, or not WordPiece, maybe BP, right, to identify the initial vocabulary. Once it is ready, then what we do? Then for every word, right, for every word present in the training set, right, I identify the base split for that word. How do we identify the base split? Base split. So for a word, there can be multiple possible splits, right? For every split, I measure the probability. The probability is essentially the multiplication of all the individual probabilities of tokens present in the specific split, right? So for every word, I identify the base split. For every word in the training set, I identify the base split. Now, for the entire corpus, meaning for all the words present in the training set, I basically accumulate all the loss together. So what is the loss? Loss is a log loss. So minus log of the probability of the split times the frequency of the word. So I measure the total loss with respect to the corpus, right? And that's my standard now. Then from the vocabulary, I identify that token whose removal will not impact the loss or least impact the loss. Okay, I can remove one such token from the vocabulary at a time, or multiple tokens from the vocabulary at a time, right? So once I remove this, again I modify the bigram. I modify the frequency table, right? Meaning the unigram table, right? Based on the modified count and so on and so forth. Then again, based on the modified count, for every word present in the training set, I again identify the base split, right? Again cumulative loss, right? And again we choose the best candidate token whose removal will not impact the overall loss, and we keep on doing this thing. We keep on removing tokens from the vocabulary unless it basically gets synced into a certain size, predefined size that you already determined at the beginning. Okay, so this is Unigram Language Model tokenization, which is used in sentence-based embedding. These are the standard tokenization methods: BP, WordPiece, and sentence-based Unigram Language Model, right? But there are lots of recent advances in tokenization strategies. Tokenization is very important to handle low resource languages, by the way. For example, those languages which are not at all present in the training time, right? The model is completely unaware of those languages. For example, let's say you don't have the resource to compute to pre-train the model from scratch for a specific language, right? We can use this kind of tokenization techniques to deal with low resource languages. With this, I stop here, and next day we basically move to the next topic of this course. Thank you.